All right. Thank you so much for giving me the opportunity to talk today. So I'm gonna sort of give an overview of what I've been up to for the last, 2 3 years now, working on both early release data from JWST and some cycle one and cycle two observations. So some for motivation purposes, I think yesterday we saw a really nice review about why would you actually care about radiation pressure on dust grains in the driving outflows. And so I just want to, quickly again drive this message that there's a lot of simulations and here's some work by here. Costa showing that here on the left is looking at the kinetic luminosity of an outflow as a function of radius as it's driven through radiation pressure on dust grains. There's plenty of times in the lifetime of this outflow that it reaches these high kinetic powers that are perhaps inducive of feedback and reaching these sort of meaningful numbers that everyone is after, where you convert some fraction of the volumetric luminosity of the quasar into an outflow, and perhaps there's effects on the host galaxy in terms of perhaps affecting the star formation properties. And so there's very efficient ways to do this with radiation pressure. And so that's one of the motivation for why I'm really interested in studying sort of the most obscure and luminous quasars, cosmic noon and sort of and above. So I just want to introduce quickly, Caroline briefly talked about this yesterday about the extremely red quasar population. Just want to kind of make a clear introduction into what they are and how they were selected. For the most part, there was sort of serendipity detected in the Sloan Digital Sky Survey, but the sort of the agreed upon criteria to select these objects now is that their I minus Y3 color is supposed to be greater than 4.6. And then there's a second criteria is that the equivalent width of the carbon-4 line in the UV has to be greater than 100 angstroms. And so once you take this criteria into account, if you look at this black curve here, this is the stacking of all the ERQs that we know about in the Sloan Digital Sky Survey. You get this spectrum that looks incredibly bizarre. I remember it's still the first time that I seeing this, and I was like, whoa, all the line ratios here, for example, between nitrogen 5 and Lyman alpha are very different from what you see in the typical blue quasars, which are shown here in red and green, and these are either matched in I magnitude to the ERQs or in luminosity. And so the other peculiar thing is that ERQs don't have strong wings emission. They're more sort of boxy in terms of the lines, and in some cases, if you can kind of see here, you also show evidence of outflows and absorption, very similar to Barberson line quasars. Sort of show this. The other population that I've been studying is the odd dust obscured galaxy sample, or hot dogs. These are even more obscure than extremely red quasars. They're sort of on average about a magnitude fainter in the restream UV, and they were selected from the WISE survey, where essentially in the shorter WISE bands, they're either marginally detected or completely undetected, and there's a really strong detection at 12 and 22 micron, and that this comes from the really hot dust in these systems, sort of about 1,000 Kelvin scale. And if you do the selection, you basically get a sample with an average redshift of about 2.5. So you are selecting immediate redshift, high redshift quasars, and you're selecting very, very luminous objects because they have to be strongly detected in the 12 and 22 micron. So the other thing is that, as we now know, a lot of these extremely red quasars and now also a lot of the hot dogs have very, very fast outflows in their system. So this is one of the sources that I've been studying. So just to highlight the width of some of these lines. So this is looking at oxygen 3, H alpha, H beta, and then the darker blue curve, that's carbon 4. And so we're seeing velocity width on the order of 10,000 kilometers per second, where you integrate about 90% of the light. But the wings go out to, in this case, out to almost 14,000 kilometers per second. And I believe this is one of the fastest outflows that we detected in warm ionized gas. But this is also, arguably one of the most luminous quasars that we know about. So this is kind of one of those like really, really extreme cases. And so perhaps maybe we should now update this plot with our previous object. This is now looking at the velocity width as a function of quasar volumetric luminosity. So the ERQs and hot dogs sort of live in the space up here. that object that I just showed should actually be a little bit above here. So yeah, we are now starting to find even more extreme objects with JWST spectroscopy. So one of the interesting questions, at least for the early release science program with JWST that I've been involved with Q3D, was to sort of try and attempt to answer if these fast alphas have any sort of impact on the ISM or CGM of these quasar-host galaxies. And so that was one of the sort of driving motivations behind the Q3D program. And so I'm just listing all the people that were involved here, and I'm going to focus on the results of the Redshift 3 ERQ that we studied as part of this program. So part of the ERS program was that all the teams were supposed to deliver some sort of software package. So for us, we developed this Q3D fit routine that does essentially PSF subtraction, but also fitting all your favorite emission and absorption lines in rest frame optical, UV, and even in the near and mid infrared. And so we have we can somewhat easily, I would say, install our code. And there's example notebooks on the website that you can go through. And hopefully on Tuesday next week, Caroline and I are going to give a brief overview of what the software does. So if anyone's interested, please join us. So here's an animation after doing PSF subtraction on this Redshift 3 extremely red quasar, and this is stepping through the oxygen 3 line, and you see a lot of very, very, very interesting kinematic structures, and it actually fills the entire field of view of this 3 by 3 arc second field of view of near spec. So we detect essentially 3 very distinct kinematic components in this object. And so one of the things that Q3D does is it allows you to see those individual components and make, for example, integrated intensity map. This is for oxygen 3. You can look at the radial velocity and velocity dispersion. This is focusing on the component that's associated with the quasar-host galaxies. So that's systemic velocities within plus minus 500 kilometers per second and relatively narrow gas. As Caroline showed yesterday, the source has a really powerful, we think, quasar-driven outflow, and that's based on sort of energetic arguments, and it has a relatively larger velocity dispersion than the rest of the system. The extent of the outflow is out to about 10 kbc, and the velocity dispersion you get in some parts out to almost 1,000 kilometers per second, so it's quite turbulent. And then just briefly want to also highlight, Caroline showed this yesterday as well, there's a number of companion galaxies to this object. This is the third kinematic component, and so I just highlighted the locations of these companion galaxies. And this is sort of narrow gas, but as we saw at much larger velocities relative to the systemic velocity of this system. So I just want to go back and focus now a little bit on the outflow in this system. And one of the goals of our program was to try and understand, is there any sort of interaction between these fast outflows in these systems and either the interstellar or the circumconvective medium? So these top plots over here, what we're looking at is in the background, it's a line ratio map. In this case, between sulfur 2 and H alpha, and then over here it's between oxygen 1 and H alpha. And what we're able to detect is this sort of enhanced line ratios that are essentially in a direction perpendicular to the quasar alpha, which is shown here in the white contours. It also happens to be perpendicular to the ionization cone of the source that we've known prior with ground-based data, and then we reconfirmed it again with JWST. And what we see, interestingly, so if we just look at the regions that are perpendicular to the outflow, we see these trends where at a higher velocity dispersion in the kinematic component that's associated with the quasar-host galaxy, we see an enhanced in these line ratios. And in red here, these are models of radiative shocks that sort of predict that at larger velocity dispersions, you expect to see larger line ratios in sulfur 2 versus against H alpha, and same with oxygen 1. And so this is really good evidence for shocks in the host galaxy of the system. And energetically, we think that the quasar-driven outflow is possible that it could be driving those shocks. This is, I think, some of the very first strong evidence that we do see at high redshift the interaction between the outflow and the interstellar medium. We've known about this in sort of a handful of nearby galaxies, But the challenge at high redshift, one, is that we didn't have the sensitivity to try actually map these fainter lines to these larger extents, but also the source has, I think, a favorable geometry where perpendicular to the ionization cone, you're actually able to see the emission from shocks, which could be orders of magnitude fainter than photoionization from the quasar. So this combination of sensitivity and also the fact that we're selecting a source that could potentially have channels where you're effectively in the shadow of the quasar ionization cone. So we have this sort of nice cartoon that we drew for the source. So we have this outflow, and then it goes in the same direction as the ionization cone. We actually do detect some evidence for star formation in this region. And what's interesting is that the dust extinction in the star formation region actually allows self-shielding from the ionization cone, from the quasar, and then perpendicular to the ionization cone is where we see the shocks. And we labeled some of the companion galaxies here with these orange ellipses. And then, as Caroline was showing yesterday, on much larger scales, we do see tidal tail features. And now with cycle, I think it's 2 nearest data, we now have evidence for even more companion galaxies in the system. So we do think that this is all happening perhaps in a core of a protocluster at a redshift of 4. So then moving on, so I about a year and a half ago joined this project to try and do similar science, but now for a hot dust obscured galaxy. So I'm listing some of the people that have been involved over the years in both the discovering these objects and then trying to get both JWST and other ground-based observations, for example, with ALMA, to try and understand what's happening in these very intriguing, very luminous, but quite obscure sources at high redshift. So here's a similar source to the one that I just showed before. This is now at a slightly higher redshift of 4.6. And these are the two line maps that we made for this object. This is looking at oxygen 2 and in the optical UV, and then H alpha. And we detect for this object very extended nebula on sort of scales of about 40 kiloparsec. And in this case, actually, based on previous ALMA data, we knew that there should be a quite extended emission. So we actually had to do a mosaic mode. So this is a 3x2 mosaic with near spec. So that was a bit of an interesting way to do data reduction. A bit of that. It was not a fun time, but what's interesting is that when you integrate essentially make a spectrum by integrating over all the nebula, we see something that's very, very peculiar. So this is showing here in the black spectrum, is that it's very much consistent with low ionization. So I think when I just joined this project, I thought to myself, oh, the brightest line is going to be O3, and we're going to see this nice ionization perhaps from the quasar, as we've seen in other systems at lower redshift. But what's interesting is that we do see this sort of low ionization nebula. In fact, oxygen 2 is brighter than O3 in the system. And then in the orange, it's that nuclear spectrum from sort of the central spaxel that shows a really, really, really fast outflow on the source. So here, just quickly, just want to show the velocity map. This just again integrated at O3. This is the radial velocity, and then this is the velocity dispersion. What's really interesting is that you may notice that in the center of the nebula, instead of this roughly 10 kiloparsec region, we see a very high or relatively high velocity dispersion. So that's indicating that there's quite turbulent gas in the system. And so similarly, I did this exercise where I looked at now the line ratios between nitrogen 2 and H alpha, sulfur 2 and oxygen 1 against the velocity dispersion. And very similarly, we see these trends where at a higher velocity dispersion, we see an increased enhanced ratio. And again, this time a little bit more in depth, confirming that if you take the mappings radiative shock models, you can actually explain these line ratios quite well, making some assumptions about the metallicity, which I can talk a little bit more about, but yeah, it definitely, as we found, is a little bit dependent on metallicity, assumption of the metallicity of the gas. So this is again just another diagnostic plot that we came up with. where now we're just plotting the low ionization line ratios against each other, and then you have the mapping models here. It's contours essentially, and then if we just focus on this one, so the points are now color coded to velocity dispersion, and so the more purple points are where you have the higher velocity, it's purple to orange, and then the really dark points here, these are coming from companion galaxies in the system, and these are, well, not so much consistent with shocks, but in fact are most consistent with star formation in these systems. But there's a lot of these points that are very, very much consistent with low ionization due to radiative shocks. What's really even more interesting is that now if we look at the line ratio versus distance, we do see that this concentration of elevated line ratios, again, this is color-coded to velocity dispersion, so the brown points is velocity dispersion greater than 200 kilometers per second. That is really concentrated in this roughly 10 kiloparsec nebula surrounding the obscured quasar. The dashed line here, this shows the effective stellar radius of the quasar host galaxy. So what we're really seeing are evidence for shocks now, not just on the interstellar medium scales, but also on circumgalactic medium scales, because we are detecting shocks that are on scales larger than this, stellar extent of the host galaxy. And in my opinion, that is, I think, a fair definition of where you're starting to reach the circumgalactic medium. And again, these line ratios here at a lower velocity dispersion are from some of the companion galaxies that we're detecting in the source. And there's different ways to count how many of them there are, and we think there's probably about like 5 or so in the field of view, and we have different ways of arguing for why we think there's that many. The other thing that's, again, going back to this point of this low ionization nebula is we actually just look at the traditional VPT diagram where it's just O3H beta versus mentioned 2H alpha. A lot of the points that we detect do not coincide with where we would expect photonization from quasars, which are these black curves here based on models. Again, assuming some metallicity. But also in the actual quasar host galaxy and in the surrounding region, we don't see a whole lot of evidence for photonization by O and B stars either. A lot of these points that are consistent with ionization from recent star formation actually comes from these companion galaxies that are on larger scales, and you actually do see a nice trend here, which we would expect based on where you would expect star-forming galaxies to lie. And the other line ratio that diagnostics basically confirm the same picture, where the central nebula, this 10 kiloparsec region, is lacking these really high ionization photons that you would expect either from star formation or quasar activity. And so the question is then, well, what is driving the shocks? I think energetically, this outflow here is quite favorable. I mean, the outflow rate is about 2,000 solar masses per year. It's quite high. The momentum flux is really high, and you only need something like less than 1% of the kinetic luminosity of this outflow if it gets transferred into the sort of the turbulent energy of the shocks that we see. You can explain the shocks in the system, and then we also try to maybe better understand what's driving this outflow. And it's very much consistent with radiation pressure on dust grains, and I'll show it in a little bit why we think that's actually a really good assumption to make for this particular object. But so we think perhaps it's this really fast outflow in the center that's maybe driving these shocks, but it has to perhaps do this in a very obscured region where the ionizing photons from the quasar are not making it out to large distances. So we had both NeoSpec data, which is what I was just showing here with IFU, but we also had MIRI data for this object. And so for the rest of the talk, I'm going to briefly highlight the most recent results that we got from that data. And so just a few thoughts about dust and outflows, sort of to set up this new detection that we have. So for a large fraction of the sources that we know where we see molecular outflows, we sort of know that dust has to exist to we form these small molecules that can easily get destroyed. So I think lots of systems in the literature that do show these high momentum flux ratios between the kinetic luminosity of the alpha and the quasar bolometric luminosity. And I think in the assumption has been, well, we're seeing the molecular outflows. Well, there has to be dust there, but the direct proof for dust is quite challenging. We do have systems where, through, for example, the Balmer decrement method in the alpha, where you see AV values exceeding 1. So there has to be dust, but how do you actually directly see it and study its kinematics? In the nearby universe, I'm actually surprised we haven't looked at M82 yet, given that it's Thursday. But anyways, this is the latest image with Webb, where in orange, in this biconical alpha in the system, the orange emission is coming from PAH. And I forgot to mention in the previous slide is that we think that polycyclic aromatic hydrocarbons, or PAHs, are actually really good sites for formation of molecules. While they're like the smallest dust grains that we see, but in terms of surface area, this is something that I just very recently learned. They're actually really good sites for formation of molecules. And at least in the nearby universe, we do have several of these examples where there are good evidence for pHs and outflows. But at high redshift, this has been sort of very, very difficult to do. And now with JWST, I think because of the higher spectral resolution power of MIRI, for example, we can start to maybe perhaps detect some of these sources. This is looking at this exact same hot dog that I just showed before. And in the MIRI spectrum, and this is rest frame wavelength of about 2.8 to 4 microns, we see this feature, which is consistent with absorption from PAH, from the 3.3 and from the 3.4 feature that most of you have probably seen in the mission. And so when we model these features in a very similar way that it's done in the Milky Way, we actually see that there's a blue shift in all these features. So these arrows here are shown by approximately how much we actually have to shift these Gaussian fits, which are to the individual carbon-hydrogen emission or absorption in this case that's produced in the source. And we measure a velocity offset of about 5,000 kilometers per second. So this is a dusty outflow moving at around 5,000 kilometers per second. As far as I'm aware, this is one of the fastest dust or molecular outflows that we've seen. And now with MIRI, the nice thing is that we can perhaps try to do this for other objects as well. In absorption, I should comment that in nearby LIRGs and ULIRGs, you only see this absorption feature in the most obscured of the LIRGs and ULIRGs that host AGNs. This is perhaps a feature that requires you to have really hot dust to actually observe. What's also kind of crazy is that if you look at the profile of the ionized emission in the source, where we see the dip in almost all the lines that we can trace, that is at the velocity of this hydrocarbon dust feature. So we think perhaps there's some link between the dust that we're seeing in the MIRI outflow and the ionized outflow in the system, and perhaps maybe the fastest outflow that we observe is interior to this dust, and so there's some extinction that is happening, and so that's why we see these asymmetric, really asymmetric. The other thing that I just wanted to comment is that the dust that we see in absorption is very, very similar to what we see towards the galactic center and also towards this O-star. And so just again for comparison, so in the shaded region, this is our model of this absorption feature. And then in blue here, this is what we see towards the galactic center. So the actual aromatic and aliphatic dust that we're observing in this object at redshift 4.6 is remarkably similar to what we see towards the galactic center. And I just want to also highlight, this is what it looks like if it's at rest frame. And so you do see that this blue shift is quite measurable in our data, given the large velocity that it has. And just briefly, just to make some statements on how we think this dust is driven. We think it's driven through radiation pressure. So I've been working with some theorists now to try to explain how you actually drive this dust. So very preliminary, we do have predictions basically on what the expected velocity is as a function of radius for an alpha that's driven through radiation pressure on dust. And so you can reach these really high velocities up to 8,000 kilometers per second if you have this high volumetric luminosity source. We're also starting to predict now what the optical depth should be for the individual aromatic and aliphatic hydrocarbon absorption features. And so we think that the outflow is likely driven somewhere around 10 to maybe 15 parsecs. And the peak of the optical depth is, in this case, for example, somewhere between 20 and 40 parsecs. So it is quite close to the actual central region of the quasar. And the acceleration is, I just want to comment, is very, very gentle. It's only 1.8 times 10 to the minus 2 centimeters per second squared. So, the acceleration due to gravity on Earth is like 980. So this is a very, very, very gentle acceleration. So that's perhaps why the dust grains aren't getting destroyed. And then you're also doing it through radiation pressure from infrared photons. We're going to talk a little bit more about some of the structures next week, but the point here is that we think that the source is highly obscured, and we have this sort of thin, narrow region from where the ionizing photons are able to escape. A lot of the obscuration is perhaps happening into this dusty outflow. So I'm going to leave some of my conclusions and thoughts here, and I'll take any questions. Thank you.
Yes.
Thanks a lot for the presentation. I had in mind to ask you something like the last slide that you presented, so thanks for already clarifying that. But I have a curiosity. So a question that is very naive, but so why should be outflows more frequent or obscuration enhanced in outflow system? So dust should be there already before the outflow, right? Yeah. And dust is radiation driven, moved by the outflow. So one question is, why should be outflows system more dustier? And so which is the effect on dust of the outflow? So you expect it to be becomes warmer, so to re-emit in the infrared in a stronger way? These are the two questions.
So I think in terms of emission, I think for the most part, now I probably should have included a slide on the actual SCD that we now measure for the source. So we think that the warm dust is reprocessed emission from the UV and X-ray photons from the diffusion dust, right? Whether there is any additional heating because you're accelerating, I'm not too sure. That's something. There's probably an opposite effect where the dust cools as it moves farther away because the radiation field right gets weaker. And perhaps that's why in some of the really obscure sources, their SCDs are in the mid-infrared are very, very flat looking.
Then they become...
Yeah, so perhaps maybe that is actually an indication of a dusty outflow itself. But aside from that, yeah, I'm not entirely sure what the physics are on the actual cooling of dust as you're expanding.
Had 2 points. Like one of them was about the outflow kinematics. I wonder if using this very low velocity dispersions in the outflow is just a geometric effect, like the outflow is perpendicular to the line of sight. It's
for the
well resolved.
The dusty outflow?
No. The earlier on when you were looking at the kinematics of the outflow and the velocity dispersions.
Right.
So if the outflow is perpendicular to the line of sight, I guess you would expect low velocity dispersions. So you get a high velocity dispersion at the center is.
I think the high velocity dispersions are in the center for that source, and I think we show at least the outflow velocity, which includes the velocity dispersion as a function of radius, and it's roughly on average flat in the inner sort of 4 to 6 kiloparsecs, and then you do start to see a drop. And that perhaps maybe because it's slowing down, maybe there's like less turbulence on larger scales, but at least on smaller scales, it's not just geometric effects. I think that there's actual intrinsic, high turbulence.
But in the center, it'll be beam smeared, right? So
this is much corrected for beam smearing effects. We have removed the point source emission from the quasar. That if we had left it in there, yeah, you would see a much higher velocity dispersion in the center. This is for the most part is quite well resolved. So the effects of beam smearing, I think, are maybe not so significant for this. The other thing to mention is that the line center doesn't shift a whole lot in this object. It's majority of the part where we see the outflow. It's actually quite broad in nature, and the actual offset relative to systemic is not crazy high.
Yeah, the question that I had was about the dusty outflow, as you say. I wonder if so you see at low redshift like these polar dust features on very small scales. We're talking about something on tens of parsecs,
Yeah.
right? So roughly torus scales, and so I mean, what are the prospects for linking those things? Maybe.
I was thinking of that might be it for like the analog for a more luminous obscured object at high redshift. Maybe that is the polar dust, right? Because there have been other independent confirmation for at least for the hot dogs that a large fraction of them are highly at least the covering fraction of the UV and X-ray emission is really high. Something like maybe like 10% of the UV light actually makes it out less. So yeah, so potentially in the outflow can be driven quite easily for this high of a bolometric luminosity given the dust opacity. So
You see like that a 3 to 5 micron bump that you often see for the dusty.
So the only feature in the 3 to 5 micron that deviates from a perfect black body is that absorption feature. The continuum is almost explained by a 1000 Kelvin